Dear students, last time we discussed the existence of unique solution to retarded differential equation x dot of t equal to ax of t plus bx of t minus r plus f of t. It is linear equation and it is non-homogeneous. In this lecture, we discuss the dependence of unique solution to phi and f. Further, we discuss characteristic equation of homogeneous linear equation x dot of t equal to ax of t plus bx of t minus r. We study the expression of solution in terms of solutions of characteristic equation. This part is very similar to ODE course. Let us start. First, we discuss Gronwall lemma or Gronwall inequality. This is very useful in our next result. Gronwall is name of mathematician. This result allows one to bound a function satisfying certain integral inequality by the solution of corresponding integral equation. There are various types of Gronwall's inequalities. Here we discuss very basic Gronwall inequality. So statement of lemma is as below. If u and alpha are real valued continuous functions, on closed interval AB and beta greater equal 0 is integrable on the same interval AB with u of t less equal alpha of t plus integral from a to t beta of s u of s ds. Here t is in the interval AB. Then u of t is less equal alpha of t plus integral from a to t beta of s into alpha of s e raised to integral from s to t beta of tau d tau. Tau is integration variable ds. Here again t is in closed interval ab. Okay, so consider this first inequality. This is called integral inequality because it contains integral. So here u of t is appearing on both sides, left as well as right. Okay, so if we assume equality here, then this is called as integral equation. Okay, and in second inequality, u of t is appearing on the left side only. Okay, so using this inequality, we can find bound on u of t. Okay, so this is importance of Gronwall lemma. So given thing is u of t is less equal alpha of t plus integral from a to t beta of s u of s ds, and here bound is of this form: u of t is less equal alpha of t plus integral from a to t beta of s alpha of s e raised to integral beta. Let us prove this inequality. Yeah, there is another part also before proving this. This is first part of inequality. If second part is if in addition alpha is non-increasing, then u of t is less equal alpha of t multiplied by e raised to integral from a to t, lower limit is a, beta of s ds. Okay, so this is quite simpler than previous. Okay, so if alpha is non-increasing function, sorry, it should be non-decreasing. Okay, so alpha is non-decreasing. If alpha is non-decreasing function, then we can rewrite this inequality as u of t is less equal alpha of t into e raised to integral beta of s ds. Limits are from a to t. Okay, so in first inequality, limit is from here, it is s to t. Okay, s is integration variable. Okay, so this is quite simpler inequality, and we are going to use this inequality in our next result. Let us prove this result. This is a very important result, so we are going to see the proof also. Define r of t to be integral from a to t beta of s u of s ds. Okay. Therefore, dr by dt equal to differentiation with respect to t. So it is simply beta into u. Okay. So dr by dt is beta into u. That is beta of t into u of t. Okay. And now given thing is u of t is less equal alpha of t plus integral from a to t beta of s u of s ds. Now this integral beta of s u of s ds, it is r of t. Okay, so we can write this as less equal, this beta of t is as it is into u of t is less equal alpha of t plus, okay, beta of t multiplied by this one is r of t. Okay, we can write this because even thing is u of t is less equal alpha of t plus integral from a to t beta of s u of s ds. Okay, this is given thing, and this is nothing but alpha u of t is less equal alpha of t plus r of t, and we are using it here. Okay, beta of t multiplied by u of t is less equal beta of t into alpha of t plus beta of t into r of t. This is by assumption. Therefore, d by ds of r of s into e raised to minus integral from a to s beta. Beta means beta of say some dummy variable tau, beta of tau d tau. Okay, it doesn't matter. If we can write here beta of tau d tau. Okay, so writing simply beta is also fine. So this is equal to, we are using product rule, dr by ds. This will be common, e raised to minus integral beta, then minus r of s will be there and differentiation of this e raised to thing. So it will be again as it is, and then differentiation of this minus integral from a to s beta. So differentiation is simply beta of s minus we have put here. Okay, so beta of s, common term is e raised to minus integral a to s beta. Okay, we have used product rule. Now dr by ds minus beta of s r of s. So this thing t or s doesn't matter. Okay, dr by ds minus beta of s r of s. So we are taking this term to left hand side. So it is less equal beta of s into alpha of s. Okay, so this square bracket is less equal beta of s into alpha of s into exponential. Now we integrate this inequality from A to D. Okay, integrating from A to D, we get. What about left hand side? We are integrating from A to D. This is differentiation, so it is r of s into e raised to minus integral a to s beta. Okay, limits are a to t. If we put lower limit, then this is e raised to integral a to a. That is e raised to 0, that will be 1. And this will be r of a. What is r of a? R of a is 0. Okay. So lower limit will give 0. What about upper limit? Upper limit will be r of t into e raised to minus integral from a to t beta. Okay. So left hand side is simply r of t into e raised to minus integral from a to t beta. Okay. Note that beta is not constant, it is function. But for simplicity, we are writing beta. Less equal. What about right hand side? We are integrating from a to t. Okay, so simply we write integral from a to t beta of s, right hand side, as it is beta of s alpha of s e raised to integral a to sorry, this is integral, there is minus and minus integral a to s beta. This can be rewritten by interchanging limits. Okay, so minus we can skip and we can write s to a. Okay, this is same as integral from s to a beta. Okay, and this is ds. Okay, now we can multiply this inequality by e raised to minus integral from a to t beta. Okay, if we have inequality and if we are multiplying by positive number, then inequality will not change. Okay, and we know that exponential cannot be negative. Okay, so e raised to minus integral from a to t beta is always positive number, and we can, if we multiply this inequality by this number, then it will be unchanged. Inequality will be unchanged. Okay, so therefore r of t is less equal integral from a to t beta of s alpha of s. Okay, we are multiplying by e raised to this thing. Okay, and this is free from s. Okay, so we can write this anywhere on right hand side. If we take inside the integral symbol, then also it will not cause any problem. Okay, and so here is e raised to integral from s to a beta, and this is if okay, so we should multiply by e raised to plus integral a to t beta. Okay, so this will be e raised to integral s to a plus integral a to t. Okay, s to a plus a to t. So that will be s to t. So it will add up to e raised to integral s to t. Okay, beta. Okay. So r of t is less equal integral from a to t beta of s alpha of s e raised to integral from s to t beta ds. Okay. Now u of t is given thing, but our assumption u of t is less equal alpha of t plus this r of t. Okay, alpha of t plus integral from a to t beta of s u of x ds, that is r of t. And now we can use this inequality here. Okay, this is less equal alpha of t plus r of t, and r of t is less equal this integral from a to t beta of s alpha of s e raised to integral from s to t beta ds. And this is what we wish to prove. Okay, our aim was to prove u of t is less equal alpha of t plus integral from a to t beta of s alpha of s e raised to integral s to t beta. Okay, beta of tau d tau. So this we have proved. Now second part, that is we need to assume that alpha is non-decreasing and we have to prove this. Okay, so let us see. So this proves first part. Let us prove second part. Here we have to assume alpha is non-decreasing. Now assume that alpha is non-decreasing. Therefore, alpha of s is less equal alpha of t for s less equal t. Okay. If we take two numbers in the interval ab, s and t, such that s is less equal t, then alpha of s is less equal alpha of t. Okay, because alpha is non-decreasing. Further, let us observe one thing. What is d by ds of e raised to integral from s to t beta? It is first thing exponential, so it is as it is exponential integral from s to t beta. Okay, multiplied by derivative of this thing integral s to t beta, d by ds of this thing, differentiation under integral sign. Okay, beta is say beta is beta of tau d tau. Okay, so it will not contain s, but the lower limit contains s. The only lower limit contains s. So what we do in this case, we differentiate this lower limit with respect to s. So derivative is 1, ds by ds is 1 into, we put minus sign because it is lower limit, and then we put beta of lower limit. Okay, so beta of s, so it is simply minus beta of s. Okay, upper limit is free from s, beta is also free from s. Okay, so this is differentiation under integral sign, that is beta of s. This is important thing, beta of s multiplied by e raised to integral from s to t beta is equal to, okay, so we can take minus sign to left. D by ds of minus e raised to integral from s to t beta. Okay, so this is important observation. Okay, now we substitute this in first part. Okay, so therefore by first part, u of t is less equal. That is first part. U of t is less equal alpha of t plus integral beta of s alpha of s e raised to integral. Okay, let us rewrite this inequality and then use what we are getting. Okay, u of t is less equal alpha of t plus integral from a to t alpha of s beta of s e raised to integral from s to t beta ds. Okay, now given thing is alpha is non-decreasing. Okay, so alpha of s is less equal alpha of t for s less equal t. So here if we are writing ds, that means s is integration variable and it is between a and t, means t is greater equal s in this case. So for this alpha of s we can write this alpha of s is less equal alpha of t, and once we write this, we replace this by alpha of t, then we can take this outside the integral symbol. Okay, so it will not depend on s. So this is important step. This is less equal alpha of t. Here also it is alpha of t. Okay, we may take common into 1 plus. Okay, we are writing this alpha of s is less equal alpha of t and it is taken outside this square bracket as a common. Okay, so plus integral from a to t beta of s into e raised to integral s to t beta ds. Okay, so here we use this thing. Okay, alpha of s is less equal alpha of t. Now second thing, beta of s into e raised to integral. Okay, so we can use this as d by ds. Okay, so right hand side is equal to alpha of s as is and multiplied by 1 plus integral from a to t, and this we can write as d by ds of minus e raised to integral s to t beta ds. Okay, now this is integral d by ds. Okay, so this is equal to alpha of s into, sorry, it should be alpha of t, it should be alpha of t into 1. And what about this? Here we take minus sign outside, integral d by ds. So it is e raised to integral s to t beta, limits are s equal to a to s equal to t. So this is equal to alpha of t into 1 minus, when we put upper limit s equal to t, then this is simply e raised to 0, that is 1, then minus lower limit, here is again minus sign, so minus minus it is plus sign, e raised to now s equal to a, so integral from a to t beta So this one gets cancelled. And what we get, left hand side is u of t. Okay, therefore u of t is less equal alpha of t into e raised to integral from a to t beta. Okay, and this proves second part also. That means we prove the result. Okay, this proves the result. Now we see our main result. Theorem. Suppose that x of phi f is the unique solution of x dot of t equal to ax of t plus bx of t minus r plus f of t and x of t equal to phi of t in minus r to 0, closed interval minus r to 0. Okay, this is solution obtained as in the existence uniqueness theorem in our last lecture. Okay, using method of steps. So this result, what this result says, then there exist constants a greater than 0 and b greater than 0 such that mod of x of phi f of t is less equal a e raised to bt into norm phi plus integral from 0 to t mod f of s ds. Here t greater equals 0, where norm phi is nothing but supremum of mod of phi of theta. Theta is dummy. Theta belongs to minus closed interval minus r0. Okay, so supremum of mod of phi of theta, theta in closed interval minus r0. This is norm phi. Okay, so this shows how this solution depends on phi and f. Okay, so bound on this solution is given in terms of phi and f. Norm of x of t. Okay, so last time we discussed what is mean by x of phi f of t. So we can skip this phi comma f. This just means that this is solution of this problem with given function f and given initial data phi. Okay, phi and f are given, so we are writing here. Actually, itself shows that x depends on phi and f. Okay, so we can say that if x is solution, then mod of x of t is less equal a e raised to bt into norm phi plus integral from 0 to t mod of f of s ds. Okay, a and b are positive constants. Let us prove this result. We are going to use second part of Gronwall lemma. We call this problem as 1. Since x, that is x of phi f, satisfies 1 for t greater equal 0, we have, so what we do here, we integrate this equation from 0 to t. Okay, so that left hand side is x of t minus x of 0, and x of 0 is phi of 0. Okay, and what about right hand side? It is simply integration of this. Okay, so we are integrating this. So left hand side is x of t minus x of 0, that is phi of 0. We take to right hand side, so that it is equal to phi of 0 plus integral from 0 to t into ax of s. S is integration variable, plus b, excuse me, phi of 0 plus integral from 0 to t ax of s plus b x of s minus r plus f of s ds. Okay, so we are integrating this equation. This is for t greater equal 0, and as usual it is phi of t, x of t is phi of t for values, negative values, t in minus r 0. Okay, therefore for t greater equal 0, we are going to find bound. So we take modulus mod of x of t, it is mod of right hand side. Okay, and then we take mod separately to each term so that it is less equal. Mod of phi of 0 and mod of phi of 0 is less equal norm of phi. Okay, we have seen that norm phi is supremum of mod of phi of theta for all these thetas in closed interval minus r 0. So this value mod of phi of 0 must be less equal norm phi, plus here we take integral modulus inside the integral symbol. Okay, so this is integral from 0 to t. First we take the term f of s, so mod of f of s ds, then next is plus integral from 0 to t mod a mod of x of s ds, and third term is plus integral from 0 to t mod b mod of x of s minus r ds. We call this as 2. Okay, now we simplify the last term, that is integral 0 to t mod b mod of x of s minus r ds. Okay, this mod of b is constant. We simply work on this mod of x minus r. So let us see. Now integral from 0 to t mod of x of s minus r ds equal to So we use change of variable. We put z for s minus r. Okay, so if we put z for s minus r, then dz is same as ds, and limits will change. Our s is from 0 to t. So when s equal to 0, z is minus r. When s equal to t, z is t minus r. Okay, so this integral is minus r to t minus r mod of x of z dz. Okay, now we can add something to right side and write this as less equal. This is less equal integral from minus r to t minus r mod of x of z dz plus I'm adding some non-negative term. So this is bigger than this thing. I'm adding integral t minus r to t mod of x of z dz. Okay, so we are adding this quantity which is non-negative, so we can write this is less equal. Okay, now we split integral on right hand side from minus. Okay, so this is integral from minus r to t minus r and t minus r to t, so it is from minus r to t. Okay, so this is integral from minus r to t mod of x of this. Z is dummy variable. We can write any such variable, so let us write down s, doesn't matter. Okay, mod of x of z dz is same as mod of x of s dx. Okay, now we split in three terms. Okay, sorry, we split in two terms. We write this as integral from minus r to 0 mod of x of s ds plus integral from 0 to t mod of x of s ds. Okay, now when s is between minus r and 0, then x of s is same as phi of s. Okay, and we just have seen that mod of phi of s is less equal norm phi. Okay, so this we can write less equal. For this we can write norm of phi. Okay, and so this is simply integral minus r to 0 ds, that is s. Okay, upper limit is 0, lower is minus r, so it is r. Okay, plus integral from 0 to t norm of x of s ds. Okay, so we are going to use this thing, integral from 0 to t mod of x of s minus r ds is less equal this thing in 2. Okay, so we replace third term. Of course there is mod b. Okay, so we can multiply mod b on both sides. Mod b is positive number, so inequality will not change. Okay, so using this into we get using this into we get left hand side of 2 is mod of x of t. It is less equal norm phi plus integral mod f of s ds plus integral mod a mod x of s ds plus this thing, so mod b into this right hand side. Okay, so we rewrite this norm phi plus integral from 0 to t mod f of s ds plus integral from 0 to t mod A into mod of x of s ds plus mod B into mod phi into r. Okay, this thing, this term, and plus this term, we can take mod B inside, plus integral from 0 to t mod B mod x of s ds. Now we simplify this. We can write right hand side as 1 plus, okay, mod norm phi is common, so 1 plus mod B into r multiplied by norm phi plus integral from 0 to t mod f of s ds. Okay, so we call this first term as alpha of t plus integral from 0 to t. We take these two terms together. Okay, mod A plus mod B. Mod A plus mod B into mod x of s ds. Okay, so this is similar to Gronwall inequality. Okay, instead of u we have x mod of x of t. Okay, so Gronwall in Gronwall inequality we had u of t is less equal alpha of t plus integral beta of s u of s ds. Okay, so if we call the first square bracket as alpha of t and this mod a plus mod b as beta, then this alpha is non-decreasing. You can see one is mod b is positive, r is positive, norm phi is non-negative, of course. This is also non-negative. Okay, so this alpha is non-negative. So by second part of Gronwall lemma, we have u of t is less equal alpha of t into e raised to integral beta from a to t. A is 0 here. Okay, so 0 to t simply. Okay, so let me write by using, therefore by using second part of Gronwall lemma, we have mod of x of t is less equal alpha of t. Alpha of t is this square bracket 1. Okay, 1 plus mod b into r multiplied by norm phi plus integral from 0 to t mod f of s ds. This is alpha of t multiplied by e raised to integral from 0 to t beta of s ds, but beta of s here it is simply constant mod a plus mod b. Okay, so what about integral from 0 to t mod a plus mod b ds? It is mod a plus mod b into t. Okay, so e raised to mod a plus mod b into t. Okay, so we proved this result with particular values of a and b. What we wish to prove? There exist constants a and b such that mod of x of t is less equal a e raised to bt into mod phi plus integral 0 to t mod of f of s ds. Okay, so we write down what are our a and b. Okay, so the result is proved, therefore the result is proved with a equal to 1 plus mod b into r and b equal to mod a plus mod b. Okay, ae raised to bt into what actually we need one more step, but it is not difficult. Okay, so ae raised to bt is common in bracket mod phi plus integral f. Okay, so this 1 plus mod b r into e raised to, okay, e raised to this thing is common. Okay, so here we are taking this outside. Okay, here the term is absent, but we can write less equal and put this term which is bigger than 1. Okay, I think I should write that thing. Okay, so let me write 2 more steps. So this I am writing, right hand side is less equal, this is there e raised to, okay, mod a plus mod b into t, it is there. I'm taking this common, that is 1 plus mod b r, okay, in bracket, this is mod phi plus this integral 0 to t mod f of s ds. Okay, I'm able to write this. I'm not saying these two right hand sides are equal, I'm saying this is less than or, okay, here we are multiplying this second term by 1 plus mod b into r, which is bigger than 1 plus something. Okay, mod b is positive, r is also positive. Okay, so 1 plus something, so we are multiplying by 1 plus mod b into r and writing new thing to be bigger than this old thing. Okay, and taken common. Okay, so therefore the result is proved with a equal to 1 plus mod b into r. Okay, a e raised to bt and b equal to mod a plus mod b. Okay, so a e raised to bt into mod phi plus integral mod f. Okay, this proves the result. Thank you.